Hello, and welcome to this video. In this video, we're going to be looking at Lenz's law. So we've looked at a few effects of magnetic fields now. We've seen that we can have the motor effect. So the motor effect, if we remind ourselves, was where we had a current causing a force. So this was from the very first video where we had that current carrying wire between those two magnets causes a force so that the reading on a scale will either increase or decrease. And in the previous video we looked at the dynamo effect, which is the opposite way around. So we have a force causing a current. Now there's a slight issue with this. If we have a situation, right, let's go back to the beginning and say that we have these uniform field lines. So this is my magnetic field, and I have, so this is my north and this is my south magnet, and then I have some wire, and we said that it has some amount of current. Let me put B here, and let's say it has a current I that's traveling upwards. Okay, now this is going to produce a motor effect. Now the motor effect, we said, was the left-hand rule. Okay, so we had the left-hand rule, and the dynamo effect was the right-hand rule. Okay, now from the left-hand rule, we can say that if we have a B field coming this way, so this is B, and we have a current traveling up here, then which direction does our force act? And I'll leave it to you to prove to yourself that actually when you line this up properly, you should get a force that acts into the page. Okay, so now we've got a current that's induced some sort of force acting on this, but now we have the force, so surely that force should now induce more current. And if that force then induces more current, that either means that we've made charges out of nowhere, which obviously we know is not possible, or we're just speeding up all of the electrons in the system, which then means that surely by this logic we then have infinite energy, because we've kind of just turned on a supply, had a magnetic field, and now we've got a force that's been produced that's caused more current, that's causing more force, that's causing more current, and it's going to just exponentially increase. And this would then require infinite energy, and this is not possible. This is why we have to change the direction of this rule. We have the right-hand rule instead. So now we need to look at this force using the right-hand rule. So let's label this as left. Now let's look at the right-hand rule. If I now have the right-hand rule, so the force here is coming into the page. So this is still the force, but this is now, and this is still the B field even, this actually means that the current has to come down here, okay? Meaning it's in the opposite direction of the current that we already have. Therefore, we're conserving energy. We're not constantly accelerating current in the same direction. If anything, this is kind of an issue because it means that we actually have opposing currents. We have two different directions of these currents, which are going to eventually cancel each other out. But we have this constant loop still, so we still have now a new current, which is going to create a new force, which is now going to go out of the page because it's in the opposite direction, which is then going to cause a new current, which is going to go back into the page. So actually these two forces here must be equal to each other because they're basically being used to cause each other, right? So we have one current that's traveling in one direction, causing a single force going down, and we have the other current that's being caused by that force going in the opposite direction that's pushing the wire back up. So if we have the same magnitude forces coming down and up, we end up with no overall motion. We have balanced forces, so this leads to balanced forces. And if we have balanced forces, that means we either have no motion or a constant velocity. So it's either stationary or constant velocity. and we know that from Newton's first law back in AS. Okay, so this is the idea that we have now, right? Lenz's law is something to do with the forces and the currents and this kind of thing. But how do we formally put a kind of definition on how would we describe what Lenz's law is? And Lenz's law states, so let me write this out formally. So Lenz's law states that the direction of an induced current, so we're causing a current, and obviously this would be the same as saying the direction of an induced force. The direction of an induced current is such that it opposes the change that caused it. Okay, and this is Lenz's law. The direction of an induced current is such that it opposes the change that caused it. Hence, what we're saying, if we go back up to this example here, if I've induced this current by this force, the direction of the current must induce a force that's in the opposite direction to that force. I'm opposing that change that initially occurred. Now, from here we have to kind of identify why is this important? Why do we actually have to care that this is a thing that happens? Surely if nothing moves, it doesn't make any sense for us to worry about it. But actually this is a very important law because, like we said, this actually is conserving the energy, right? So this ensures the conservation of energy, even though it doesn't seem like it does, because I'm effectively saying that I'm using energy to create a force, and that force is being converted back into energy, which is being converted back into force in a constant loop. I'm not creating any energy, I'm not destroying any energy. I end up with the conservation of energy. This is the biggest reason why we have to know this, but there are obviously other implications of Lenz's law. The probably most common one being that it's trying to oppose the change. If I want to put an object inside a magnetic field, for example, we said in the previous video that if I have a bar magnet and I want to induce an EMF in this coil of wire with n turns, let me draw that a little bit better, I had to move it back and forth in order for it to cross the flux lines, in order for it to change the magnetic field strength that's passing through the surface and therefore induce an EMF. However, I'm now inducing some current, which is therefore going to induce a force, which is then going to have the opposite effect to what actually caused it. Therefore, if I'm saying that I have if I were to draw this in, my initial force is to go inwards, you can actually prove that it will produce a force that means that the coil itself, or the magnetic field produced by that coil, is going to actually push the bar magnet back out of the coil. If I'm trying to push it in, the coil pushes it out. And now this means, so if the magnet is forced towards the coil, this then, in order for it to induce a force coming backwards, means that there has to be some sort of magnetic field that's created by this. Okay, so if the magnet is forced towards the coil produces a force to push it away. And this is an implication of Lenz's law. So this is why we can't just have infinite energy from these things, because it's actually because we're pushing in, forcing towards it, the coil itself is going to push back. Okay, so it's using some of that energy that we've just tried to convert to electrical energy to actually push back, which means we can never get 100% efficiency because of Lenz's law. Now, this is kind of interesting because that means that if we're pushing away a magnetic force, we are pushing it back with another magnetic force. It means that the coil itself, the solenoid, acts as a magnet, which means it has to have a north and south pole. Now, if we know that it's going to try and push it away, we can then decide which way is going to be the north and south pole. And actually, it turns out that this side is going to be north because they're going to repel each other, and this side, therefore, is south. And you can then say that this will have its own field lines because this is now essentially just a bar magnet, right? So this then means that we will end up having some sort of magnetic field from just a coil of wire. And this is the whole idea of electromagnetism. By inducing an electric field inside the coil of this wire, by having charges moving, I then have a magnetic field that's produced as a result of that. This is why we can combine the two. Now, if we say that we overcome this force, or we can push for long enough that we get a constant velocity, we reach a terminal velocity, and it gets inside the magnet, that would surely mean that as soon as it's inside the magnet, so if we scroll down and take, or inside the coil, sorry, so it's inside the solenoid, so let's say the bar magnet is here, and this is originally the north and this is the south. If I'm going to keep pushing it this way, now the coil doesn't want it to leave because it's now been pushed past the point. The change at this point would be to take the coil out, surely, right? So that means that the bar magnet now or the solenoid no longer wants the actual bar magnet to leave. So what happens is it has to flip sides because the bar magnet itself still has this north side here and this south side here. And so if this were to stay, and let me try and draw this like this, if the solenoid wants to keep the bar magnet inside, at this point, if it were to leave it, this would then just have a force, so the north gets attracted to the south, and it would just be kind of accelerated out of here, and so it would gain energy. We know from Lenz's law the whole point of this idea is to try and conserve energy, so it can't gain it, which means that if it wants to now exit this loop, the poles now have to change. Now, in order for the poles to change, it means that the direction of the current now has to change. Okay, so it means that halfway through, if we were to push the bar magnet the whole way through this solenoid, the current changes direction. And so if we have current changing direction, it means the poles of this, so the poles change polarity. So the north becomes south and south becomes north. And that then leads to us having Lenz's law back. It means that if I try to push the north towards the north, it's going to repel. If I try to push the south towards the south, it's going to repel. We have to then put in enough energy to actually push it out of this at a constant velocity, since the forces will always find themselves balancing. Now, the key part with this currently is this fact that the current has to change direction, okay? Now, you can model Lenz's law in any way that you wish, and you will find in all cases that you will have to have a current that is changing direction. Now, this is going to link back to the electromagnetic induction as well. When we come up with an EMF, it's always a sinusoidal EMF. That's what we saw when we looked at rotating coils. It means that from all of these induced EMFs that we're getting, they're mostly for what we're going to look at are going to be alternating currents, okay? Because from these ways that we are generating electricity by rotating a coil, we only ever get alternating current. If we push inside and outside, we get alternating current, because we say here the current has to change direction by Lenz's law. And from the spinning coil, we found that it was a sinusoidal EMF, which means it's a sinusoidal current, and therefore we have alternating current in both cases. Now, alternating current is something we're going to look at in a later video, but for now, we can now conclude that we know how electromagnetic induction works. We can now prove that the motor effect and the dynamo effect don't equal infinite energy, because we have these currents traveling in opposite directions and the forces acting in opposite directions because of Lenz's law, and this then concludes electromagnetic induction. Thank you for watching.